Thank you very much. Well, a very good afternoon, everyone. And I'm sure by this time, we are all quite convinced that hypothermia added to radiotherapy really works. We have been hearing a lot of things from various aspects, whether it is the in vitro studies, whether it's modeling, and therefore it makes us convinced that yes, it works. Great. But then the problem comes that as a clinician, I need to apply what my colleagues from the lab convey to me. And when I have to use this to my patients, I need to think, what is the best strategy? And when I talk about strategy for radiotherapy, I mean strategy in terms of the fractions and schedules, in terms of the number of fractions, in terms of the dose per fractions, and in terms of the total dose. Because classically, we all have been working on a model again, that's the linear quadratic. And in the linear quadratic model, we go with the biological effective dose. And that's where we compare treatment strategies. And in that linear quadratic model, without a time factor, it's simply an expression of ND, which is the total dose, and then in the brackets 1 plus d by alpha beta. The small d, of course, is the dose per fraction we know, but then the question comes that the entire BED is determined by only one variable which we are not certain and which we try to extrapolate from the lab, and that is alpha beta. So the entire story just remains on one factor, alpha beta, and therefore it's important for us to now realize that what happens to this alpha beta when hypothermia is added to radiotherapy, because that's how we would like to make the best use of the dose fraction schedule to get the optimum results. So just a schematic cartoons of what actually, when we're talking about this alpha beta, I'm sure most of them are known to you. So what we have is a radiation cell kill, which is a double strand DNA break, a lethal damage, which leads to an alpha cell kill. The other is when the radiation dose kills is there, but then they cause a single strand DNA break, which leads to either a sublethal or a potential lethal damage, and that's the beta cell kill. So one is a non-repairable, and the second, as we just heard, is a repairable. So in a linear quadratic function model, this is what we all are knowing, that this is what happens, and the alpha beta value is taken where the alpha cell kill and the beta cell kill are supposed to be equal. So if that is so, then if the alpha cell kill is more, then it would lead to a higher alpha beta value. It's simple maths. On the contrary, if the beta cell kill is more, which is a repairable damage, it will lead to a drop in alpha beta. Simple maths again. Okay. So now what happens with hypothermia? We know it's a potent radiosensitizer. We know it inhibits or is sensitive to the hypoxic tumor cells. And we also have seen just now even that it inhibits the repair of the radiation-induced DNA damage. So the single strand DNA break of the sublethal or potentially the damage, the repair of it should be inhibited by hypothermia, and therefore would lead to a higher beta cell kill. If that is so, it should be expected to reduce the alpha beta value. Okay. So till now, we are just making assumptions. And here is what our colleagues from the lab tell us. And this is one of the excellent papers which I came through from Amsterdam Medical Center, where they studied the effects on the linear quadratic parameters with hypothermia and radiotherapy. And so that's the curve with radiotherapy and moves toward this side with hypothermia, and these are the values for various cell lines
And this is the treatment, 41, 43 with hypothermia or sham, alpha values, beta values, alpha beta values, beta effectivity. And what can you see here is that the alpha beta values without hypothermia was about 13.8, drops down to about 3.3. So there is a really decrease, and that's because the beta effect actually goes extremely high. And that's what we expect to do. So hypothermia results in the fall of alpha beta, and this is primarily due to the enhancement of beta. So if this is so, does it also happen clinically? And that's what perhaps we need to share. So the study objective was that we all are assuming that the tumor alpha beta is usually taken as 10. For late toxicity is taken as 2.53, except for some cases like prostate it's taken as 2.5 or 1.5, melanomas may be lower, but usually, I'm talking about usual stuff, it's taken as 10. And that's how we all calculate the BED. So then, can we estimate the clinically alpha beta? Now, clinically alpha beta from studies which use hypothermia radiotherapy versus radiotherapy, and I've taken 3 specific examples: recurrent breast cancer, locally advanced head and neck cancer, and cervix cancer. So the study population consists actually of 3 published meta-analyses, which we did for breast, head and neck, and cervix. And all these studies were selected based only if there were definitive RT dose mentioned, the number of fractions mentioned, dose per fraction mentioned, and all these patients were uniformly treated with once a dose fraction. And we checked on the endpoint of only complete response for the first part of the study. So if we do that, there were 12 trials totaling about 864 patients. Complete response with hypothermia and radiotherapy was about 70% compared to 43% with radiotherapy alone. And that's the forest plot. And as you can see here, for cervix, head and neck, recurrent breast, it doesn't show any heterogeneity. Yesterday there was some concern about the heterogeneity. So there is no heterogeneity because all these studies uniformly show that hypothermia improves the complete response, and the risk difference is about 0.28, which means 28%. So now, let's try to compute the BED with RT using the standard alpha beta value of 10. Now, if there are better complete response with hypothermia, it means that hypothermia actually improves the biological effective dose. So you have a higher BED. So if that is so, then the BED HTRT would be the BDRT into the percentage difference per percentage CR of HTRT versus percentage of CR by RT. And now, since the N and D values are same, so you can use the expression from the LQ model and then try to compute what would be the alpha beta HTRT from the simple model, where you know the D, and you know the computed BED from HTRT. And therefore, using this, we could estimate the alpha beta separately for each of these 3 sites. And this is the table which shows the alpha beta values here for each of these studies. And what you can see that the mean BED ranges from about 64.7 with HTRT is 109.5, and for all patients the alpha beta is 2.25. And this is what happens for recurrent breast, 2.06 mean value, head and neck 1.7, and around 3 for cervix. So now the question is that we have done it for complete response. So does it also apply when we look at the long-term outcome of these patients? Because that is more crucial. So we looked at some of the data of ours for the bladder cancer, which are not from this particular group. So invasive bladder cancer, we looked at the BED and then computed the BED alpha beta here as 15 because that's what the value given by Majewski was there, and then try to compute, assuming a BED 3, that is the thermobiological BED. And if we do that and look at the long-term local disease-free survival, we don't find any difference when the BED is more or less, which was quite surprising. But now, if we change the alpha beta value to 15, and compute the thermoradiobiological effective dose, there is drastic change. It certainly means that your alpha beta changes from 15 to 3 by adding hypothermia. That's what we saw for this subset of patients. Yeah, I'm just finished, last slide. So to conclude, hypothermia induces by inhibiting the repair. It leads to increase in the quadratic components. It reduces the alpha beta values, which we see from cell survival and also from the clinical trials. And finally, if that is so, a reduction of alpha beta is now here seen to be congruent with the in vitro data, and this certainly is because of the beta cell kill higher, and certainly these can be used for computing the dose fractions in clinical practice. Thank you.
Thank you.
This is actually the paper which is not coming up.
We got time for one burning question, if there is. If not, maybe I can.
I have a quick question.
Okay.
Classical radiation biology teaches us if tumors have a lower alpha-beta ratio that we should use hypofractionation. It can be the case with melanoma, some other tumor, prostate. So would you suggest then perhaps we should consider designing hyperthermia, combination radiation, kind of doing hypofractionation regimen instead of standard fractionation of 2-grade perfraction?
That's what actually it hints. That if the alpha beta drops down to 3, it's better with the hypofractionations.
Okay. Okay, thank you. Leroy?